Hi everyone, my name is Zhongda Li. I'm the Senior Staff R&D Engineer at United Silicon Carbide. Today, I would like to welcome you to the webinar, Silicon Carbide FETs, Easily Driving Higher Power Density. So let's get right to it. First, I'd like to give you a brief introduction to the products of United Silicon Carbide. We have Silicon Carbide Schottky diodes and Silicon Carbide JFETs and the Silicon Carbide FETs. So the Silicon Carbide FETs, they are normally off devices, and they are made with a Cascode technology. We co-packaged high-performance Gen 3 Silicon Carbide JFETs with Cascode optimized silicon MOSFETs. Thanks to this structure, they are the only standard gate drive silicon carbide devices in the market today, meaning that they can be used in a silicon gate drive from VG off 0 volts to VG on 12 volts. So this product family has 650 volt and 1200 volt products. In terms of choices of RDS on, we provide the lowest from the lowest 7 milliohm to the highest of 150 milliohm. So a lot of choices for your design. These FETs has excellent body diodes. So the body diode has very good reverse recovery, very low QRR even at high temperature. And the body diode VF is much lower than typical silicon carbide MOSFETs. So these VF are below 2 volts, more like a silicon MOSFET. It has very good gate drive compatibility, meaning that you can use a silicon gate drive from 0 to 12 volts. But they also work with silicon carbide MOSFET gate drive, such as -5 to +20 volts. In terms of thermal performance, they have very low R-theta-JC thanks to the superior silver sinter technology used on the die attach. And also they have very good ESD rating because we have actually integrated the ESD protection diodes to the device. And the TJ max rating is 175 degrees C. In terms of choices of the packages, we have a lot of choices for you. The newest to the family are the DFN 8x8, but today we would like to focus on the TO247, both the 4-lead and 3-lead, because we have just released these new products, 7 milliohm and 9 milliohm, very low RDS-on devices in these packages. So why do we care about low RDS-on devices? Well, the simple answer is it reduces the DC conduction loss. And this is very important for the lower switching frequency applications because there the DC conduction loss can be the dominating factor. And the second reason for the pursuit of low RDS-on is we can push discrete solution to even higher power level, which used to be only viable using modules. So this means you can reduce the system cost by using discretes. Or if you don't want to push the power level, then you can use less discrete devices to parallel less devices than your current discrete design solution. So that's also a good thing. And thirdly, for module makers, these low RDS-on chips can be made into modules, and the lower RDS-on per chip means less chips to parallel. So that simplifies the module layout and I think makes the design also easier. So United Silicon Carbide expands the boundary of the ultra-low RDS-on FETs. Now we're offering in the industry standard TO247 package for 650 volts, the lowest RDS-on we're offering is 7 milliohm, and for 1200 volt we're offering 9 milliohm. So these are great new parts, and I would like to introduce today. So for today's agenda, first I will introduce the new UF3SC series silicon carbide FETs with RDS-on below 10 milliohm. And then we will actually tell you how we achieved this. We will show you the Cascode technology secret sauce. because we understand that the designers would feel more comfortable if they understand the internal works of the device that they are designing in, instead of just looking at it as a black box. And in the end, we will show 4 applications where this low RDS FETs will really shine. That's the EV inverter, the fast battery charging, the solar inverter, and the circuit protection. And in the end, we will show where you can find design support and the content on our website, and followed by the Q&A session. Now, here are the 4 new silicon carbide FETs we are introducing today, which we believe are the industry's lowest RDS(on) device inside the TO247 package. So they come with 650 volt and 1200 volt. For 650 volt, we're offering the lowest RDS(on) to be 6.7 milliohm at room temperature. For 1200 volt, we're offering 8.6 milliohm for the lowest part, and also we're offering a 16 milliohm part as well. So they come in TO247. So the 1200 volt, we have 4 lead and 3 lead. And for the 650 volt, we're only offering in the TO247 4 lead package. So, and if you look at the R30GC value, the thermal resistance, you can see they are really low. And this is because of the the silver sinter die attach technology used in these parts. Because we believe that for such a low RDS(on) and the high ID rating, 120 amp and 77 amp, to really use this part, you really need to be able to get the heat out of this package. So that's why we have implemented this very low thermal resistance technology in this package. So these parts are drop-in compatible with silicon IGBTs, silicon MOSFETs, because they can be driven at a gate voltage from 0 volts to 12 volts with no issue. And also they are compatible with silicon carbide MOSFET gate drive voltages. For example, -5 to +20. That's because the VGS max rating of these parts are actually ±20 volts. So that's why you have a huge margin to use these parts. And they have excellent paralleling behavior, and also they use advanced stack Cascode technology. And I will show that in more detail later. So they are well suited for inverters, high power DC-DC converters, and circuit protection applications. So how did we make this industry's lowest RDS(on) device in TO247? Now let's look at it. So next I will show you the Cascode technology secret sauce, and we hope once you understand what's under the hood of the Cascode, you will feel more comfortable and even excited to try it in your new designs. Now, the United silicon carbide FETs consists of 2 chips. One is a silicon carbide JFET, which is normally on, and the other is a silicon MOSFET. This silicon MOSFET is a low voltage MOSFET, but in this Cascode configuration, it never sees high voltage. Once the voltage it reaches about 25 volts or 20 volts, it's sufficient to turn off the JFET, and all the high voltage, high bus voltage will be supported by this silicon carbide JFET. So combining these 2 chips in this Cascode fashion, the overall device is a normally off device, meaning that when you apply 0 volt to the gate, the device is off, and when you apply let's say +12 volts, then the device is fully on. Now, based on this, we even made this stack Cascode technology, meaning that we put this silicon MOSFET on top of the silicon carbide JFET. And this chip can be packaged into a discrete, like today's TO247 4 lead, or they can be used as a bare die and packaged into modules. So this chip stacking really reduces the footprint and simplifies packaging. But still, the question is why Cascode with silicon carbide JFET can achieve this ultra low RDS(on). Why it's so hard for silicon carbide MOSFETs? To understand that, we need to further zoom in and look at the internal device structure. So here shows the schematic cross-section view of a generic silicon carbide MOSFET and united silicon carbide JFET with this low voltage silicon MOS. So here is the total Cascode structure. So for certain voltage rating, let's look at the major internal RDS(on) components. So for a given voltage rating, the drift region, which is the voltage supporting layer resistance, is about the same. Either it's a silicon carbide MOSFET or it's a silicon carbide JFET. And so is this JFET region. So this resistance is also about the same. However, in typical silicon carbide MOSFET, there is this R channel component, and this is a problem. This component is very high due to poor silicon carbide MOS channel mobility, which is about 10 times worse compared to silicon MOS. And at 650 volt, this R channel can be over 50% of the total RDS(on). And if you look at the united silicon carbide FET, now we don't have this R channel component, and it's replaced with this silicon MOSFET resistance. This is a very small number. By our design, it is usually less than 10% of the overall RDS(on). And compared to the R channel, this is much, much lower. And that is how united silicon carbide FET achieves such low RDS(on). And once we understand this device structure, we can further see some other unique benefits of the Cascode structure. So the first one is gate drive compatibility. Now, again, on the left here is the typical silicon carbide MOSFET. So it requires a negative VGS to turn off, for example, -5, and also a higher voltage above 15 volts to fully turn on. And this is also because it has this silicon carbide MOS channel. So that is just the material property of this channel. And for the same reason, the maximum negative VGS is usually limited to -7 volts, shown in this plot here. So this plot here on the right shows the maximum VGS rating. The left is the recommended operation VGS. And this -7 volt is usually required to avoid a threshold drift towards 0 volts. And if you apply to negative VGS in the off state, then the threshold could drift towards 0, and you could have some reliability concerns. Now, looking at the united silicon carbide FET, the operational VGS is 0 to 12 volts, and that's why it's compatible to silicon standard gate drive. And the maximum VGS rating is ±20 volts, which is same as the typical silicon IGBTs or JFETs, or sorry, silicon MOSFETs. So this is really good. This is a much more robust gate and more compatible to a variety of gate drives, including silicon or silicon carbide. And this is all because the gate signal is actually applied to this silicon MOSFET. And the silicon MOSFET MOS gate has been very mature in terms of technology and reliability. So what's beside the gate drive compatibility? So another benefit of the Cascode would be the body diode. So here again shows the typical silicon carbide MOSFET and the body showing the body diode, and on the side is the united silicon carbide FET. So first, let's look at the typical silicon carbide MOSFET. Now, this body diode is made of silicon carbide, and it's a PN diode. So due to the wide bandgap of silicon carbide material, this body diode VF is very high. So it's usually higher than 3.5 volts. Another drawback of this body diode is the QRR. So this QRR increase very fast with temperature increase. So here shows the measured silicon carbide MOSFET QRR at 150 degrees C, and you can see it's quite high. It's 220 nanocoulomb. And if you have to use a silicon carbide Schottky diode as an anti-parallel diode, then that further increased the QRR to 275 nanocoulomb. But for united silicon carbide FET, the body diode here is made of silicon. So what you see here is, so in the third quadrant, reverse conduction, the current flows through the silicon MOSFET body diode, then through the channel, these two resistance components inside the silicon carbide JFET. So in the silicon carbide JFET just behaves like a resistor, and all the body diode is from this low voltage silicon MOSFET. Now I want to emphasize low voltage because you may heard of silicon MOSFET. High voltage MOSFET has not so great body diode performance, but for a 20-30 volts low voltage MOSFET, the body diode performance is excellent. And you can see here the DC conduction, the knee voltage is 0.7 volts, which is what you expect for silicon, any silicon diode, PN diode. And the DC conduction loss at rated current is only 1.5 volts. And further, this QRR here at 150 C is only 105 nanocoulomb. And this is because the silicon MOSFET itself QRR is very low, and second, this QRR is just part of it is just the capacitive charge of the JFET, and that's why it doesn't go up with temperature. So now you may ask, since the Cascode is 2-chip and is being co-packaged, does it take larger footprint? The answer is no, not with the stack Cascode technology. So like we showed in earlier slides, what we do is we stack the silicon MOSFET on top of the silicon carbide JFET. This way, the silicon MOSFET does not take any footprint in either the die pad or the DBC. Further, using the Cascode, we can eliminate the anti-parallel silicon carbide Schottky diode, since the body diode of the Cascode is so good. The VF is so low and the QRR is so great. So here we show the example for a small DBC using united silicon carbide solution. We can pack 6 of these stack Cascode chips and parallel them. However, for the same DBC size, if you use typical silicon carbide MOSFET, you might need to use a silicon carbide diode if the module will go into reverse conduction. And in that sense, you can only pack 3 of these silicon carbide MOSFETs instead of 6. So using this stack Cascode technology, we can increase the module power rating without increased footprint. And united silicon carbide would be happy to supply stacked chips to module makers and do a collaboration. So now, for next, let's look at where these ultra-low RDS(on) devices really shine. In our opinion, they opened up several new design possibilities in the EV inverter field and the fast battery charging, solar inverter, and circuit protection. So let's get into the details. So for EV inverters, let's look at how these ultra-low RDS(on) parts can help you design the next-gen power module, and even possible to build them at significantly reduced cost with parallel TO247 lead discrete devices. So we did a paper design looking at the traditional IGBT plus diode solution using 1200 volt devices, silicon devices. The chips would be 100 amps chips, 4 each, and with a bus voltage 800 volts, switching frequency 8 kilohertz. So this solution would be able to achieve 200 kilowatts with 98.5% efficiency. Then we look at using 1200 volt UF3SC 1200 volt 9 milliohm devices from United SiC Carbide. It's easy to see that you can achieve much lower loss. So for example, if we use 2 of these devices at 200 kilowatt, you can see that efficiency is 99.3%. Very good. And if you want to further reduce the loss, you can use 6 of these devices, and at 200 kilowatts, it's 99.5%. And it's even possible to push the power level to 300 kilowatts while maintaining an efficiency of 98.9%. And so the previous situation was with 8 kilohertz. Now, with using the United SiC Carbide FETs, you can push the switching frequency to 16 kilohertz while still maintain above 99% efficiency. So this opens a huge possibility for future inverter designs. So you're welcome to visit our website to see more info on our technical blog. And also I would like to mention that because of the fast switching nature of these parts, it's possible that you will need to use some kind of snubber, either a bus snubber or a device snubber, to achieve the desired switching speed. And we also have some technical blogs and application notes on snubber on our website. Now let's look at one of the case studies. So this is an inverter module made by AC Propulsion using United SiC Carbide FETs for 200 kilowatt drive unit inverter. Now you can see down here these 6 1200 volt silicon carbide discretes are paralleled to form a 354 amps single phase module, and they were put into this 300 kVA inverter. And here this picture shows the inverter with no chassis, and this picture here shows the fully assembled inverter, 300 kVA, in a very compact size. And what's more is this actual measured inverter showed excellent efficiency. Now you can see the highest efficiency is 99.98, and it also has a very large area that has efficiency higher than 95%, which is 98.62%. The average efficiency 500 to 2000 RPM is 97.64%. So this is really amazing result using United SiC Carbide 1200 volt TO247 40 discrete. The second application is high current battery charger. Now if you look at the circuit here, on the primary side, typical application for low voltage battery charging system would be IGBTs with Schottky diodes in parallel, and on the secondary side would be just the diodes. Now we have this 650 volt 7 milliohm device. We believe using it you can get much higher efficiency compared with the IGBT based system. So let's do some calculation. For 100 amp operating current with 50% duty cycle, The conduction loss using the IGBT plus JBS solution, just on this JBS diode, the conduction loss would be nearly 100 watts, assuming 2 volts drop at 125 degrees C at operating temperature. Now, looking at our device, the 7 milliohm 650 volt FET, using synchronous rectification, the dissipation was only 45 watts. That's 0.9 volts drop at 125 degrees C. And further, on the secondary side, if we can also use the synchronized rectifiers to replace the secondary side diodes, and that can dramatically cut the total loss and heat burden of the system. So that's an excellent choice for bidirectional designs, because to make bidirectional designs, these secondary diodes has to be replaced with FETs. The third application is solar inverters. Now let's look at this paper design of a 60 kVA solar inverter using the new parts. So we look at 3 different topologies: the 2-level, which uses one of the 1200 volt 9 milliohm device per switch, 2 per phase, so that's 6 devices in total. The second topology was a TNPC, so that used 2 of the 9 milliohm 1200 volt and 2 of the 7 milliohm 650 volt per phase, so that's 12 devices in total. And the third is the NPC topology, which used 4 of these 7 milliohm 650 volt devices, also 12 devices in total. Excuse me. So looking at the efficiency curves, now if this frequency is 12.5 kilohertz, all 3 topologies showed very good efficiency, above 99%, around 99.5%. And if you push the switching frequency higher to 25 kilohertz, now you can see the TNPC shows the best efficiency. And further push to 50 kilohertz, now the 2-level start to drop by a lot, but the both the NPC and the TNPC can still maintain a very good efficiency. So this kind of 60 kVA power level is usually accomplished with power modules, but now with this new offering of the ultra-low RDS(on) parts from United Carbide, it's possible to make these design with discrete devices. The last application we would like to look at is the solid-state circuit breaker. So solid-state circuit breaker need ultra-low conduction loss, so that simplifies the design and most importantly the cooling. So for example, the solid-state circuit breakers or battery disconnect switches in EVs, they all require a very low RDS(on) device, so which is perfect for these new ultra-low RDS(on) parts from United Carbide. These new parts also has excellent paralleling behavior. I will show later, and this allows scaling to much higher current applications where modules are traditionally required. And by using discretes, then it's become more cost-effective. And on the right here is the 9 milliohm 1200 volt short circuit test waveform. So this is experimentally measured waveform, and you can see this part is capable to turn off very high current without failing. Another aspect that's very important for circuit breaker and the circuit protection applications is the high temperature robustness. So that's why we test these devices up to 200 degrees C, even though the TJ rating is 175 C. So we want to see that what happens at 200 C, and I want to make sure that nothing weird would happen. So for this device, 1200 volt 9 milliohm device, you can see that the blue curve is room temperature and the green curve is 200 C. This is the on-state ID/VDS curve. You can see the RDS(on) increased, but the IV curve still looks perfectly normal. On the right-hand side here is the leakage current. We tested up to breakdown voltage, And you can see the green curve here is 200 degrees C, and even at 200 degrees C, the leakage current is only about 200 micrams. And this is very low, and if you calculate the heating loss from this leakage level, it's nothing. So this is really good for high temperature robustness. Now we want to use this product in development to showcase the high performance in paralleling these low RDS(on) chips. This is a 2 milliohm 1200 volt small module, the SOT227 module, and you can see here this is the DBC. It has 6 chips in parallel. Each chip would be a 1200 volt 9 milliohm chip, and here on the right hand side here is the actual measured IV curve in on state, and you can see it is capable to handle 3500 amps in such a small footprint. So this SOT227 is only 28 millimeter by 38 millimeter, very compact footprint. So we achieved this by using high performance DBC to improve the RC to JC. The RC to JC of this module is below 0.033 degrees C per watt. And all the die attach interfaces are silver center, and that's also part of how we achieve this low thermal resistance. And furthermore, this bottom side of the module is gold plated, so which means it won't get oxidized and is solderable. So this whole package can be centered to a heatsink, which further reduce the thermal resistance from the case to your heatsink. So now you have it, the UF3SC series, industry's lowest RDS(on) silicon carbide FETs. So these FETs are made possible by advanced silicon carbide Cascode technology. They directly address fast-growing applications, and they opens up new design possibilities. So in the end, I just want to go show you where to find the design supports and contents. You can visit our website at www.unitedsic.com, where you can download our datasheet and SPICE models, and also you can find our app notes and white papers, also our fantastic technical blogs and videos. Also, we have the comprehensive product selector guide and many reference designs. If you have any other questions, feel free to email us at sales@united.com. Our global distributors are DigiKey, Mouser, and Richardson Electronics. Okay, so now let's get to some questions. And again, I would like to thank everyone for attending today's webinar. Thank you very much, and goodbye.